Hello, welcome to week 11. In this week, we'll be wrapping up branch and bound by talking about two more difficult application problems. These two problems do not have any efficient polynomial time algorithms, but we'll be able to show that branch and bound can provide much more efficient solutions comparing with brute force. The first problem for this week is traveling salesperson problem. The traveling salesperson problem, or TSP, is a really difficult problem. In this problem, we imagine a salesperson who has to choose a route that takes them around a cycle of n cities, visiting each city once and returning to where they started. All the cities are connected by direct roads, and all the roads have different length or costs. The goal is to find the route with the shortest total length or the smallest total cost. A small example here. There are four cities A to D. We know all the pairwise distances. Our first question is, how can we represent a candidate solution? Or how can we represent a cycle of cities where each city appears exactly once? It can be a permutation of all the cities. We can write A, B, C, D, and it goes back to A. Or another candidate solution could be B, D, A, C, B. In fact, we can start from any of the four cities and need to come back to the origin. Does it matter which one is the origin? In other words, our permutations A, B, C, D, A, and B, C, D, A, B representing different solutions? No, they're not. The order of visiting all the cities is exactly the same in these two solutions. So it does not matter which city we start with. Without loss of generality, we can assume that we start from A. And a unique solution is then a permutation of three cities B, C, D after A. And we always go back to A. So this could be one solution, and we have A, C, B, D, A. That's another solution. Next, the question is, what's the brute force algorithm for this problem? When we assume A is the origin city, the rest of the solution is just a permutation of n minus 1 cities. So there are n minus 1 factorial possibilities. In this example here, we only have 4 cities to consider, and the problem is easy, and n minus 1 factorial is not a large number at all. However, in reality, we could be looking at thousands of cities with very complex topology. As we mentioned in the previous slide, TSP is one of the most studied optimization problems, and there are many heuristic algorithms to solve TSP. If you are interested, the Wikipedia page of TSP is a good introduction to the problem and its popular solutions. However, the baseline is there are no polynomial time algorithm for TSP. Now let's see if we can provide a branch and bound algorithm for this problem. Here, as you can see, we represent the pairwise distances or costs as a matrix or a 2D list. TSP does fit the profile for branch and bound pretty well. It is an extremely difficult optimization problem, and there are no efficient polynomial time algorithms to solve it. A solution is a sequence of decisions. Again, recall that it does not matter which city we set as the origin city, since we always need to circle back, so the solution is a full circle of cities. Without the loss of generality, we assume we start from city A. In order to provide a branch and bound solution, the most tricky part is to compute the upper bound and the lower bound of a solution. So first, what's the global upper bound? We can use a greedy heuristic again. When we start from city A, we see which city is the closest, so that'll be B. Once we are at B, we check which city is the closest. Note that we cannot go back to A, even though the distance 10 is the minimum. We need to visit all the rest of the cities before we return to the origin. Also note that in the diagonal, we have all the distance as infinite. Although we know the distance from one city to itself should be 0, we use an infinitely large number here, so when we are looking for a minimum distance, we never pick the same city. From B, the next closest city will be D. Then we're at D, there is only one option left. So that'll be C, and then we'll go back to A. What's the cost of this circle? That'll be AB distance 10 plus the distance between BD, that's 25, the distance between DC, that's 60, and the distance between C and A. So that'll be 15. The total cost is 110. A quick greedy algorithm will give us a decent solution. It's feasible, so we can use this as our initial global upper bound. What about the global lower bound? What's the minimum cost of a complete circle? Notice that each node is connected in the circle through two attached edges. The best case, including one particular node, is that the two edges are the ones with the minimum costs. A's two minimum edges are 10 and 15, and B's two minimum edges are 10 and 25. C's two minimum edges are 15 and 35, and D's two minimum edges are 20 and 25. So the global lower bound will be the sum of the two minimum edges for each node in the graph and divided by 2. Why divided by 2? Because we have counted each edge twice. We only have 4 cities, so we only need 4 edges. Now we have 8 edges, so we need to divide the sum by 2. 77.5, that'll be the global lower bound. The way we computed the global upper bound and global lower bound will be the same when we compute the bounds for partial solutions. Now we have the global lower bound and upper bound here. Now we start our extension. Recall that we assume we always start from CDA. For the next decision, we only have 3 possibilities, B, C, or D, and then we always go back to A. There are 2 decisions missing in the middle. Now, what's the lower and upper bounds for each partial solution? For the first partial solution, we only have one edge decided. That's going from A to B. The cost is 10. So that's the cost so far. You can write it here, 10. And then the same thing for the rest of the edges. For A, we have already picked one edge, that's 10. So we can only pick one minimum edge for A. So that'll be this one, 15. And for node B, we already have one edge decided for B. That's weight 10. So we need to pick the second minimum edge. That's 25. Now for node C, we pick 2 minimum edges. So that's 15 and 35. For node D, we pick 2 minimum edges. That's 20 and 25. So this will be our lower bound. What about the upper bound? We use the greedy heuristic again. So we have the cost so far 10, and then we pick the next one. Once we are at city B, the next smallest will be D. Once we are at city D, there's only one option left. that's C. And then we need to go back to A. So CA, that's 15. This will give us the lower and upper bound of this partial solution. That's 77.5 and 1110. We could do the same for the second partial solution. When we have decided one edge, that's A to C, we have the cost 15, that's cost so far. And then the minimum cost will be, for A, we can only choose one minimum edge, that's 10. For B, we can choose two, so we have 10 and 25. And for C, we've already have one edge, 15, so we'll choose the second minimum edge, that's 35. And for D, we can choose the two minimum edges, that's 20 and 25. For the upper bound, we use the same greedy heuristic. AC, the cost so far is 15, and from C, we choose the next minimum, that'll be B, and the cost between C and B is 35. And from B, we only have one option, that's D, so the distance between B and D is 25. And then from D, we go back to A, the distance between A and D is 20. So for this partial solution, the lower and upper bounds are 77.5 and 95. And similarly, we can compute the bounds for the last partial solution. And the bounds are 80 and 95. Now looking at these two new partial solutions, we see that the most promising one is this. It has the smallest lower bound, so these two have the same lower bound. It's a tie. However, this one has a lower upper bound. So this one looks the most promising, and we will go ahead and extend this one. This solution was also able to lower the global upper bound to 95. Now we extend the second partial solution, and then we can cross it out. And the two possible extensions are these two. So same idea, we can compute their upper and lower bounds. Notice that these two solutions are actually complete solutions, because once we have decided ACB, the fourth city will have to be D. And for this one, the fourth city will have to be B. You can compute their complete costs. That's 95 for this one and 110 for the second one. We know immediately that this solution is higher than the global upper bound, so it cannot be an optimal solution. We can delete it right away. Now we have 1, 2 partial solutions for extension. We'll repeat the same process until all possible partial solutions are either extended or eliminated. Oftentimes, you'll see that people use a tree to represent the idea of branch and bound. So in the root node, we have the starting city, so that's A, and we can compute the global lower and upper bounds. And then the next step, we have three possible extensions. We go from A to B, from A to C, or A to D. These represent the three partial solutions we had before. Same idea, we can compute the lower and upper bounds for each possible extension. And then we look at all three of them and see which one is the most promising, and we further extend that solution. We compute their lower and upper bounds. Now we see if we can eliminate any partial solution. If that's the case, we can delete that branch completely, and then out of the other live branches, we look at the one that's the most promising and repeat the expansion process. To wrap up, the traveling salesperson problem is extremely difficult. The decision version of TSP is NP complete. It means we don't have any polynomial time algorithms to solve this problem. Branch and bound with good heuristics can significantly reduce the number of extensions. In the example we showed in the slide, we only have 4 cities, so you might not really see the power of branch and bound. But when you have a large number of cities, hundreds or even thousands, you will see branch and bound will be able to eliminate a substantial portion of partial solutions without extending them to complete solutions. The TSP branch and bound algorithm still fits the pseudocode we talked about last week. However, the greedy heuristic for computing the upper and lower bounds is more complex to implement. This branch and bound algorithm is definitely non-trivial to code. If you have the time and you are interested, please go ahead and implement this algorithm in Python 3. Okay, that'll be all for this lecture. I hope you enjoyed this problem and its branch and bound solution. I will see you in the next lecture.